So our final session, multiple membership models. So what are these? So these are models which are used when for example, the students don't belong to one school, rather the student is changing school over time. Okay, so it can be used in a pupil mobility analysis. So we want to study student outcomes. We want to take into account the fact that students are nested within schools, but over time, like between the start and end of secondary schooling, some kids have attended 2 different schools, some 3 different schools, and the proportion of time spent in each school varies across kids. And we want to take all of that richness into account rather than just naively assigning students to the final school they attended. Particularly, we're trying to use these school-specific estimates for school accountability purposes or school choice purposes. Or in another example, you might have students' scores in English, and maybe students have 2 English teachers, an English language and an English literature teacher. And maybe these are mixed up across the students because this English language teacher teaches these 3 classes, and literature only does 1 class, and another literature, and you're trying to pick apart and estimate individual teacher effects. Or you might have journal articles with multiple co-authors, and the journal articles have been scored for the ref. And from that information, you're trying to get individual academic quality. Yeah, there's 1 mark for the paper, but it belongs to 2 people. The ref score, 4-star, belongs to 2 academics. And then these academics split apart and write with other authors, can from all this information we pick apart. That's multiple membership. So lots of applications. So we're going to look at the multiple membership model. We will show that classification notation and diagrams again, so it'll be a little bit quicker. We'll talk about these weighting schemes. This article belongs to 2 authors, Sophia Lapesca and Anders Skrondel. They're really excellent academics. Do we give it a 50-50 split? Or do we give a bit more to Sophia, because she's first author? 60-40? What weighting scheme should we use? Yeah? I don't know. Sensitivity analysis? Does it matter? Okay. Or pupil mobility, 3 years in your first school, 2 years in your second. Weight at 0.6, 0.4? Or the second school is closer to being age 16 in the outcome. Do we need to upweight schools attended more recently? Distorting time. Again, sensitivity analysis. There might be, we're in court, we've got 3 judges, and there's a sentence dealt out, judge-specific effects from a group decision. So that's another application. So really, I think these are really fun models for picking apart individual effects. Okay, so these data, someone was saying earlier that the different methods give different answers, but they all look pretty similar. This is fictitious data where we get a really big effect of method choice. So I simulated data. Now, more generally, it's really good to learn to simulate data and fit models back. Okay, it's a really good way of understanding models. When you simulate data, you have to declare what the parameter values are. It forces you to think about how big values should be. It is how you do power calculations. If you want to do a power calculation for a t-test, you have a formula. If you've got a more complex model, there's no longer a formula, and you have to do it yourself by simulation. It's great for understanding when models fail. Why is it failing? Well, let's simulate some data where things are clean and I can see what's going wrong. So, that should be taught more, because it's very useful. And here I simulated a teaching example. Fine. So I've got students. I'm interested in a lot of research I've done is on school value-added effects. So trying to estimate school quality from student data. I've got student exam results at age 16. We statistically adjust, just like in the previous Garner and Roundup example, test scores at entry to secondary school, a baseline adjustment. And then maybe some other factors are being adjusted for, and you're trying to get closer to measuring differences in school effectiveness. So if kids are changing school over time, then surely you want to take into account that mobility to be fairer to schools. Otherwise, you might have some schools who are just off-rolling, which happens in England. Their kids, as they get close to the exams, like these kids aren't going to be good for us in the league tables. Let's force them out. Okay, and because the league tables only look at the kids at the end point, it ignores the fact that there are some kids that are earlier who are forced out, and their outcomes have been ascribed, given to a new school where they've only been there for 6 months. So that's the kind of motivation.
So I simulate data with 1,000 students and 25 schools. Lovely. Standardized outcome, age 16, standardized prior attainment, age 11. And each student attended between them 1 and 4 schools over a 5-year period. Okay, here's the unit diagram. So the dotted line are for a child who attended 2 schools. So child 1 attended school 1 for 5 years, child 2, school 1 for 5 years, child 3 attended school 1 and school 2. Maybe I could write on the numbers, 0.4 at that time in this one, 2 years, 0.6, 3 years in that school. Maybe I need to indicate the ordering. Okay. But you can see that, again, a little mechanically, you're trying to show the nature of the data. Okay. So this is important now because we need to know 2 things. We need to know for each child the sequence of schools attended. So the school ID of the first school attended, the school ID of the second attended. We also need to know, well, how long did they attend the first school? How long did they attend the second school? We need to know these school IDs and school weights for the sequence. So here I've shown that. So here, student 356 got a score of 0.93 at age 16, 0.93 of a standard deviation higher than the sample average. So they're doing pretty well. They shifted up the distribution. At age 11, they were only 2/3 of the standard deviation above the sample average. They're pulled away, moved up the ranking, if you like. So well done. And that student, 356, they only attended 1 school, school 18. The first school they attended was school 18. The second school they attended, 0. 0 just means there's no school ID. You could have maybe a missing value, if you like. And because they only attended school 18, the proportion of time they spent in that school was 100% of the time. Second child, 438, their first school was school 21, their second school was school 10. They changed schools during the 5 years of secondary schooling. They spent 70% of their time in the first school, 30% in the second. So 70% in school 21, 30% in school 10, and so on. Okay, so you need to have this information. If you only have the IDs and not the weights, then you would have to say 50-50, a third, a third, a third, a quarter, that's what you'd do. Okay, and I'll show you for these data, which are richer, what happens if you naively assume that. There's a form of measurement error. Okay, so that's the data. Now, that is one way to store the data, and it's very efficient because my school, I've got 25 schools, but my children only attend up to 4 of them. So I need 4 columns for the IDs and 4 for the proportion of time, 8 in total. Another way of storing that is as follows, where we have 25 columns, 1 for each school. This is more intuitive, but is computationally, well, it's a bigger data set and computationally could be slower later on. So here's the proportion of time that the child spent in the first school, the second, the third, the fourth. Okay, so child 356, if we go back, they only attended school 18. I don't have P18 here, it didn't fit on the slide. Okay, so but this one down here we go. So child 748 was in school 4, 25, and 23. Well, here's school 4. They spent 37% of their time in school 4, 0% in school 5, 0% in school 6, 45% in school 25. The same information. But of course, if you had a bigger data set and you had 250 schools and kids were still attending between 1 and 4, there's only so many schools you attend in a 5-year period, yeah? You still have 8 columns in this format, and then here you'd have 250. Okay. So you can do it either way. Yeah, and I think I've given the data to you in both forms. I've given you those columns and these columns, and we use them. It's the same information in 2 different ways. Some ways lend themselves more to certain things. Okay. Right.
What's the first presentation of data that you're going to reweight things based on what you're talking about before, like closest to age 15 fail, because you have ordering of what schools they went into?
Yes, you're right. This contains more information. This also has the ordering, whereas that doesn't. That's a good point. Yeah. So yeah. So yes, they lend themselves to different ways. So you could use this to kind of upweight schools closer to the exam, downweight others, distort time, distort the weights. And once you've done that, you could reshape the data here to that format, should you need that format for something else. Yeah. And I think for Stata and R, we want it in this format. Okay. In MOWIN, when I used to teach in MOWIN, it was this format. And in kind of Bayesian models, it would be more this kind of format, which is more efficient. Yeah. Okay. So, yes, it's funny this, 400 students attended one school, 300 attended two, 200 attended three, 100 attended four. Very clean data, yeah? Okay. So 60% of pupils changed schools. Realistic? No. About 7, 8, 9% of kids change secondary school in England. Okay, so this is very dramatic as to be a teaching example. Okay, but clearly in journal articles, most journal articles are multiple membership. Yeah, so here, most articles are written by 2 or more people, not by 1. Okay, but most kids attend one school. So it depends what the application is. So it's not realistic for this application, but it would be realistic to have that degree of mobility or multiple membership in other applications. Okay, so here's some notation. Right, so what we want to do here is we want to regress age 16 score on an intercept and any explanatory variables, but then we want to have a weighted sum of school effects. Yes, I'm influenced by the first school I attended, and the second, and the third. Okay, but it needs to be a weighted sum because I spent a long time in the first, a short time in the second, and a median time in the third. Yes, there's not a simple, I don't give equal weight to all the schools I've attended, I weight it by proportion of time. So these W's is the weight or the proportion of time that child I spent in school J, where J is indexing the sequence of schools attended. This notation, again, a bit ugly, personally. It's what was done in the literature initially when these models were proposed. That's what you'll see in the articles. But conceptually, it's just a weighted sum of school effects. And it's easier if you see, so here I've taken an example child, they attend, you plug in the child ID, it spits out the sequence of schools attended. They attended schools 5 and 17. And so you could substitute those numbers in. Here's the school effect for school 5, school effect for school 17, the weights of the proportion of times in each. Maybe they spent 0.6 in school 5, 0.4 of their time in school 17, and that is the model. Okay, so we've got 2 school effects for this child. There'll be 1 for the next because they didn't change school, 3 for the one after, and the school effects are multiplied by the proportion of time. Now, we're talking about methodological extensions, which are actually new research. One thing you could do here is those weights I've imposed. You could estimate the weights, or you could estimate what distortion of time gives the best fit to the data. Okay, and so yeah, that's something which you could do if you did these models in like STAN, Bayesian software in R. Here we're imposing linear time. 3 years in the first school, so you get a weight of 0.6. 2 years in the second school, weight of 0.4. And I can manually try out different weighting schemes. You could just try out a lot, and then kind of, if you try out enough, that's a little bit like estimating them, because then you could have got the BIC, and then just pick one with less BIC, and that's a form of estimating by brute force. So you could do that in this software as well. Okay. So again, that's an article. That's a new paper to do that, I think. Here is the classification diagram. Students are double arrow, multiple memberships of schools. So in the literature, you'll see classification diagrams. That's what a double arrow means. And you can see quite complex patterns with students are multiple members of schools, schools are within school districts, multiple members of neighborhoods, because you could simultaneously have kids doing residential moves as well as school moves. And so you get quite complex diagrams. But we're just doing the simplest case here. Here is just paralleling the talk we just gave. So here is, where's my child? Here's my child, okay, with a very high age 16 score. And then we're just saying how mechanically, how does the model work? Well, you start when you ignore the right-hand side at 0, and you gradually introduce the terms. Beta 0 gets you up to the average age 16 score across my 1,000 students. And then my child, they attended school 5 for 3 years. Now, if they attended school 5 for all 5 years, would get up to the line at the top. Okay, that is the mean scores for the subset of kids who attended school 5 for 5 years. Okay,
But my child also attended school 17. Well, this is the school effect for school 17. There's no weight on here. So this is the mean score for those kids who only attended school 17. Now, my child has a mixture of those two things. They spent 3 years in school 5, 2 years in school 17, and so they end up as a weighted average between those two lines, that little horizontal line. Okay, and you can see it's 60% of the way towards school 5. Yeah. Okay, so it's not bang in the middle, and that's what that is. 0.6 times U5 plus 0.4 times U17 takes you there. Okay. And was it Katie? What yeah, so she's interested in, it's not here, she's interested in endogeneity. Essentially, these models assume there's no kind of hidden processes going on. So here, might there not be an interaction effect between my first school and my second school? Yeah, they could have a clash of styles or complementary styles. Or more realistically, what happens is, sadly, disadvantaged kids are being bumped around schools. They're not, the disadvantaged kid is not in a random school. When they get bumped into another school, it's not another random school. These models assume the sequence of schools are random. You shift from one school which is struggling to another school which is struggling, correlated. So not necessarily interactions, correlated effects. These models ignore correlations, they ignore interaction effects. But if we don't do multiple membership model, then we're ignoring people mobility on top of that as well. So the models are always flawed. Yeah, so this is additive effects when they have to be non-additive and correlated.
And those would be methodological extensions, if one was to do that. Okay. Yeah, and then this is the prediction for the subset of kids who spent 60% in school 5, 40% in school 17. There's just 2 of them. And this is my kid here. So mechanically, that's how the model works. But it's only by drawing that out that you realize, like, this is kind of quite naive. I'm just going main effect, 0.6 of that, 0.4 of that, put it together. There we go. You kind of see there's more going on now. Okay, so we can fit these models by maximum likelihood or MCMC. Just like the cross-classified, we use REML when there's few clusters. I've only got 25, that's not many. I'd say if you're sub 40, where has it gone? I think it was 25. Yeah, 25 schools. I'd say, let's say around 40 schools or fewer, you might shift to REML. But you can always try it both ways if you see no difference, and there's no reason to use REML. But you'll start to see a difference, more of a difference, the fewer the schools there are. So I'm going to do REML here. I think, yes, REML here. This is, we're going to have to do the same computational tricks we did for cross-classified model with an extra tweak in Stata. In R, suddenly it gets harder for the R people. You can't do this in LMER. You have to use a kind of a wrapper function, which will mess around with matrices and feed it into LMER for you. And that's not on, you have to download that manually at this point in time, but it works. Okay. And MCMC for when you've got, actually, I've got multiple membership of schools, multiple memberships of neighborhoods, I've got school districts, family effects. Then you end up shifting into MCMC because it just copes better. Okay, so this is the model. Okay, so this, you go look at this and you go, well, hang on, George, that looks really similar to before. So remember what we had way back in the cross-classified one. You can find it here. Okay, before the break, the S's were school dummies. Okay, the child either went to school 1 or school 2 or school 17. There were 1s and 0s. Yeah, well, now we just change the 1s and 0s to proportions. That's all it is. And suddenly, so if you can do cross-classified, all you have to do is, instead of plugging in S1 to S17, we plug in P1 to P25 in the next data set, where the P's are not, I spent 100% of my time in that school and 0 there. It's all 0.4, 0.6, 0, 0, 0. That's all it is. So it's nice once you've understood the first one. That's why I went through it in a bit of detail. This is much easier. Okay, so these P's are the proportions that I showed you earlier in the inefficient form of storage. They're not zeros and ones, they're zeros and proportions. Okay, there's only a 1 for the subset of kids who are stable. 40% of kids were stables. Kids. Yeah, great. Much easier giving this talk, having given the previous one. Okay, so it's still a 3-level hierarchy. No, so no, now, sorry, I'm sorry, this is a 2-level hierarchy. Okay, because now we say there are students within my study. Yeah, so I student, J is study, there's one study, my study, and then I enter, how do I enter schools? By entering not school dummy variables, but the school proportions, the P's. They've got no regression coefficients, but they've got random slopes or random coefficients, if you like. Okay, and there's only one J, my study. We've got U1, U2 up to U25. They're here, and yeah, their variance is constrained equal, their covariances are 0. This is the between school variance. This is the within school variance. And so let's fit the model. So we fit all models by Remmel. Model 2 is the model of interest. Model 1 is the naive model which ignores clustering altogether. Its purpose is solely to give us a deviance, so that the drop in deviance is a test for whether that parameter is significant. Okay. Why do we do a likelihood ratio test for this parameter? Because if we did a naive t-test, it assumes you've got a normal sampling distribution. Variances don't have normal sampling distributions because variances can't go negative. So they have these skewed sampling distributions. You should never just do a t-test. Okay. And in R, they don't give you the standard error. They say, don't do it. Here, you could do it just manually. They don't give you the t-statistic. They do give you the standard error. So some naively do that. But you should do the likelihood ratio test. So that's what we've been doing. So the deviance drops by 115 for one extra parameter, highly statistically significant. And so my school effects are statistically significant. We do need a multi-level model. It is substantively large because you can see the outcome is approximately 1 is variance because I simulated a Z-score. And you can see 25% of the variance is between schools, 80%, 75% is within schools. So it's a big effect size, and it is also statistically significant. Okay, so actually interpreting the numbers, again, the hard bit was kind of getting to this point and estimating the model in a way. Okay, so now you might do things, well, what would happen, George, if we just naively assign students to one of their schools, let's say the last school that they're in? Okay, and this is what traditionally studies do. And we're going to see a really dramatic result because I've got simulated data which are not realistic, but mechanically they show you. But in other settings, like I said, you will have lots of multiple membership, like co-authored articles. Okay, if you just assigned every article to the first author, it's better than assigning it to the second. Okay, in some disciplines, maybe you should assign it to the last or not, you know. So, but it's not as good as giving a fair representation. So here, model 2 was the multiple membership model, the correct model. Model 3, we just did a conventional 2-level model where we did students nested within the final school attended. And look at this. Okay, the school variance is grossly underestimated. Yeah? And the student variance is slightly overestimated. So we're going to get really bad predicted school effects off the back of this. Okay, they're going to be too small. We get the impression that schools matter, they're not that much. This is saying actually they matter a lot more than we naively thought. Okay. Clearly the greater degree of mobility, the more the difference we've got a lot. What now about this? What if we didn't observe time spent with each school? And this comes back to what I said earlier. Often you'll know, for example, the journal articles, you know the authors, you don't know what portion of work the first author did, the second, the third, the fourth, and you just have to make an assumption. So rather than using, so I'm no longer going to use this information. I'm going to pretend I don't have it. And so I'm just going to have to go one, a half, a third, a quarter, so they add up to 1. Yeah, I just have to assume that a child who attended 4 schools spent an equal proportion of time in each. How would my results change? Because that's not the reality. Look, they spent more, and that's more than, less than a quarter there, less than a quarter there, more than a quarter, more than a quarter. Okay. So we'll do that. That's model 4. So model 4, it slightly underestimates the school variance. Okay, slightly overestimates the student variance. Okay. Part of the reason for that is whilst I simulated random proportions of time in each school. Okay, and they were averaging around a quarter. So that's partly why it's not such a big change. So there's a bit of measurement error. I've underestimated the school variance as a result, but actually it wasn't such a naive assumption for these particular data. It would be more naive, you could say, for journal articles where we know the first author does more work than the second author on a 2-author paper. Okay. I don't know, that's what I think. This is what happens on my articles. So, you know, so there you see a bigger difference because it's a more naive assumption. Maybe it's more realistic for mobility. And it's certainly realistic for the simulated data where I know the truth. Then you might do things like distorting time. You might go, well, okay, rather than giving equal weight, why don't I kind of upweight schools attended more recently, downweight schools attended further behind? You could do that. I haven't illustrated that here, but that's something you could do. Okay, all those models will fit the data worse than model 2 because model 2 replicates the data generating mechanism. I generated the data according to model 2, therefore model 2 will be the best fitting model. If you fit any model which deviates from model 2, it's going to fit worse. So you'll see the more you distort time from linearity, the worse it will fit here. But in reality, we don't know what the truth is. We don't know that time is working linearly. And you can explore that by cycling over these schemes. Okay. Right. I'm going to yeah, so the VPCs and the ICCs here. Okay, so the tempting thing to do with model 2 is to say, oh, the VPC, which is the proportion of variance at the school level, is the school variance divided by the total. That's what we always do, right? The subtlety here is that relates only to the subset of stable students. Yeah. So the VPC is now a function of how mobile you are. Okay. And so if students attend multiple schools, the VPC is actually going to go down. I'm not going to go through the mechanics of it. The formulas are there. I'll spare you the formula. Except to say, you know, taken to the extreme, imagine that some students attend all 25 schools, equal proportion of time in each. Okay, then they've got to then the schools can't account for why some kids do better than others. They've all had a common exposure, and the VPC drops to 0. So the more you attend multiple schools, the more the school effects kind of cancel each other out on average. You know, you went to a good school, this was less good, or that's okay, you know, and they start cancelling each other out. You only go to one school, you get 100% of that school. And if that school's a good school, you go whoosh, and the bad school, you go whoosh. You attend a sequence of schools, things cancel out. So schools as a contribution to variation in the data will be greatest for kids who stay in one school. The chunk of data relating to kids who attend many schools, it's all cancelling out. Yeah, it's not saying that school is unimportant, but if you attend a load of schools, they're all going to work against each other. Okay. Yeah. That's a bit, it's a kind of, it's just something to think about. It's in the slides and you've got the equations there, which show you as well.
It's also, as you were saying, that if somebody's attending several schools, very likely there's something else going on.
Yes.
Affecting their attainment to important data.
Yes, so what I've just said is on the naive model assumptions that you're attending a random sequence of schools. So you're at a school, you go to another random one, and the quality is just randomly changing. Reality, bad school, bad school, bad school. So then the VPC isn't dropping. So yeah, so this comes back to the models, all models are inadequate. So you'd want to acknowledge that in kind of doing these calculations as well. Okay, we've had this before, so this is diagnostics. Just check that the school effects are normally distributed. If they're normally distributed, they should lie on the 45-degree line. Okay, have people seen quantile plots before? Does this look like normally distributed? Is that good? Is it not? Any worries? You know, yeah. As a mean question, the data have been simulated from a normal distribution. That's perfectly consistent with normality. So things have to be kind of quite departed from normality for us to worry. Yeah. So again, simulating data allows you to see what's reasonable, what's not. These are the predicted school effects from the multiple membership model, where they've accounted for multiple membership and mobility. Yeah. Okay, Q3, we're almost there. Right, push through. The next model is we add a covariate at age 11 scores. And so this is mimicking what they do in England with Progress 8, which is the government school accountability system by Beta. They regress students' GCSE scores and their key stage 2, 8, 11 scores. They've got school effects, but they don't do this. They just assign kids to the final school attendance. Doesn't matter so much because only 7, 8, 9% of kids are mobile, not 60. Conceptually, it's unappealing. Might not make a difference in general, but to minority schools, it will. That is high mobility. And another thing is, the schools aren't being rewarded for the hard work that they do with kids who then leave, and so on. So many motivations for kind of trying to build in realism, and maybe to also try and fight off-rolling. If you think that if you are going to be held accountable for kids you've got rid of, maybe they'll be less inclined just to push them on, or not. So it gets into policy, even though the models, it hits policy issues. Okay, so age 11 scores go in as a baseline adjustment because kids aren't randomly assigned to schools. We need to make fairer comparisons between schools, value-added approach. So that was the Z score. So unlike the Raudenbush thing where we couldn't interpret the coefficient easily, age 11 scores are standardized, and so is the outcome, age 16 scores. So 0.49, we say a 1 standard deviation increase in age 11 scores predicts a 0.49 standard deviation increase in age 16 scores. Okay, so it's a large effect size. There's a strong correlation between age 11 and age 16. It's almost 0.5. Funny that, right? That's simulated that way. Okay. And now here I mentioned to someone, look at this. The school variance goes up when you put an explanatory variable in. Okay, that's weird. Okay, normally we explain variance away. Yeah. In a linear regression, the residual variance can only go down. R squared can only go up when you put in variables. In a multi-level model, sometimes, occasionally, the school variance can go up. So if this was real data and I looked at that, I'll go, ooh, 0.24 up to 0.26. Wow, something weird's happening there. There must be some weird selection process going on. Okay. And if you think about it, and I have thought about it previously and forgotten, so I'm glad I've written it down. What it implies is that the most effective schools were assigned the worst students. Okay. So with surgeons and mortality rates, you hope you give the sickest patients to the best surgeons, most experienced surgeons. Okay, but that's going to, if we look at everyone's outcomes, your outcomes are not going to be as impressive as they should be because you will unfairly have the sickest patients, whereas someone or a more junior will be easier to treat patient. And so your outcomes look more similar than they should be. You adjust the case mix, whoosh, you pull apart, greater variance. So that's what's happening here. The most effective schools, the best surgeons, have got the sickest patients. Okay, that's what it's implying. And you go, wow, that's really interesting. Let's write about that. It's not true. It's simulated data. That's chance variation. But you can easily kind of overinterpret numbers moving around. And that's perfectly consistent with chance variation that you can see moving from model to model when you only have 1,000 data points in 25 clusters. Okay. Adjusting for the, okay. So one last thing you could do is you could enter in mobility as an explanatory variable as well. You know, because you might expect, well, we know that mean outcomes will be lower for mobile kids than stable kids. So you could put a dummy in for did he ever move? You could put a dummy in for number of moves made. You could put in dummies for timings on moves. Did you make a move in year 7, 8, 9, 10, 11? You very richly do all kinds of things. You bring in residential mobility simultaneously. And so in the fixed part, you can actually describe mobility as well as accounting for it in the random part. So, yeah. But of course, crucially, mobility is confounded with social disadvantage. And there's all kinds of, you know, that needs to be thought about richly because we haven't put that into the model in any way at all, either the fixed or the random part. Final model of the course is going to be model 6, where, well, what about the school variable? You know, if you go back to our last model, entering student characteristic was easy. But how do I enter a school characteristic? Because each child attends multiple schools. So if I want to add, well, what is the effect of school climate on student outcome? Well, I can't just put in school climate of the final school attended. I've got to put in the school climate of every school I attended. And I didn't spend equal proportions of time at each school. So I need to put in like a weighted average of the school climate values across the sequence of schools I attended, weighted by the proportion of time in each. Okay. So that's a bit fiddly, and that is simply what we're doing there. You know, in the data, I have school climate variables, and this is the school climate value of the first school attended for that child, and 0 for the second because they didn't attend the second school. Okay, child 438 attended 2 schools, 0.7 and 0.3, so minus 0.98 for the first school. The school climate for the second school is 1.03. We need to do 0.7 times the first number plus 0.3 times the second, and that will give us the average, the weighted average. Okay, so we just do that for every kid, respecting the sequence of schools and the proportions of time of their climate values. So there's a bit of data manipulation. But once you've generated that variable, you can put it into the model. And there it is, it goes in there. And obviously the school variance explains away. So the school explanatory variable, which is a weighted average of the sequence of school climate values for that child, explains away the school variance. It does not and cannot explain away the student variance because it's a school characteristic. We can't explain why within schools some kids do better than others, because within a school, both kids are exposed to the same school climate. So you only have explanatory power there. Final slide of the course, which is just a summary. So yeah, these multiple membership models really, you know, almost just, yeah, they're really exciting, and data structures are more complex than just students within schools. You know, we have cross classifications, we've got multiple membership, we've got dyadic data structures, reciprocal type things going on. And, you know, you can try and build the model to account for these features and study them, and it's better than not doing so. And if you think about it carefully, you kind of realize that you're still making a lot of assumptions, and it's important to be very clear about those. You can include random slopes. You could have multiple memberships of schools and neighborhoods, because if you change schools, well, often it's because your family's moved home, not always. And so you can do these things. And that's it. So thank you. You've done very well. Marooned on the desert island of multi-level modeling. It's brutal. Normally I do 3 sessions in a day, and that's tough. And you've done 4. Just be glad you didn't have to do 5. I've recorded the 5th. So well done. It's been really nice teaching you all, and it's really nice for me to teach these more advanced topics, and particularly for me to learn about multi-level survey weights and plausible values. So yeah, good. Well done, everyone. Yeah.